Thank you, Martin, for that introduction, and thank you, everybody, for coming to my talk. Today, I'm going to tell you about neurosymbolic programming, which, in my opinion, is one of the most exciting new areas in artificial intelligence. I am sorry, there is a little bit of a problem with the clicker. Yeah, if you just click back.
So it can click forward from backwards?
Okay. All right, take two. So I'm here to tell you about neurosymbolic programming, which I think is one of the most exciting new areas of artificial intelligence. But before we really get into the details of this area, let's take a step back and just think about science and engineering more broadly. Through the history of civilization, science and engineering have had two important components. One of them being measurements, that you are observing the world and you are collecting data and you are operating on that data. And secondly, there's been human insights. So if you think of the sciences, you have data coming from experiments, and then the human mind comes up with theories which are then validated against this data. If you think of engineering, you have a similar story, except now maybe the human mind comes up with designs, and then you run those designs in the real world, and then you see how they work, and then you iterate through this process. Now, over the last decade or two, we have, of course, had this thing called artificial intelligence. And so there's a tremendous amount of excitement about potentially doing science and engineering using AI. So you want to replace that human part of this picture using artificial intelligence. And the potential then is pretty tremendous, right? You can imagine an AI program coming up with new scientific theories, AI programs coming up with new engineering designs, and this can have extremely broad implications for all of human society. Now, there is already some evidence that this vision is coming to fruition. So for example, just a couple of years back, some folks I know at MIT, they were able to discover a brand new antibiotic that is effective against a wide number of drug-resistant bacterial strains using a deep learning method or a kind of AI. And there are examples where you have AI being used to design chips. You all have heard of the use of AI in self-driving cars, and there are lots and lots of different applications that would suggest that this idea of having AI engineers and AI scientists, it's maybe on its way. But, and there is always a but whenever one starts in this way, that there are some problems with the current approaches to AI, which are, over the last decade or so, it's been largely machine learning. And before we get into those challenges, let's just quickly situate everybody here by just talking about what this machine learning is at a very high level. And some of you, or many of you, are already deeply familiar with machine learning, and for those of you, just bear with me for just a couple of slides. So this is what the picture of machine learning looks like. So I'm going to give a very simplistic perspective, which captures nonetheless a pretty significant set of subset of machine learning. So you're given some data, for example, think images from the internet or text documents collected from the internet, and then you have some sort of a target signal. Let's say you're talking about pictures, so you are thinking about what kinds of objects appear in this picture. Is it cats or dogs or gibbons and whatnot? And so you have these two kinds of things, and they go into this computer whose goal is to come up with a function, f, which is going to take any image, and it's going to predict what the corresponding y is, the value of this target signal. So is this picture, in this new picture, is this going to be do you have a cat or do you have a dog or some other animal? And the point of machine learning is to start with these xy pairs, a large number of them, and then discover this f, okay, using algorithmic techniques. And commonly, this discovery process is done using continuous optimization techniques such as gradient descent, which you may remember from math class. But there is a wide amount of flexibility regarding what this function looks like. There are many different possibilities. For example, you can think of f being a sort of a decision tree or a collection of decision trees, or what is called a logistic regressor. It's a concept from statistics, neural networks, which is what we are going to primarily talk about. And neural networks specifically, they look something like this. So you're starting with some inputs. So your input is a vector. This is the x that I talked about just a minute ago. And then the network consists of a series of these so-called layers. And each layer consists of a linear transformation followed by a nonlinear transformation. And so one way to think about what's going on here is that you are starting with this vectorized input, and then you are constructing essential features of this input at higher and higher levels of abstraction. So to make it very concrete, in the case of images, you may start with a collection of pixels, and then at the end of the first layer, what comes out of that layer of nonlinearities, you have a vector that captures, maybe where are the edges between the boundaries between the different objects. And then at the next level, you may have, some more high level information, like what are the main objects here. And then maybe, if you go on like this, at some point you're going to have really abstract information, like do I have a cat or a dog or a panda, and so on. So that's what a neural network is in just a very shallow way. If you want to learn more about them, there are now plenty of online courses and other kinds of resources. So two important benefits of neural networks. And by the way, neural networks are what's running the world of AI now, which in case you didn't know this, this is what those neural networks look like in a simple case. And the key benefits are that a representation like this can approximate really any function that you can imagine between vectors. Even though this looks like a very simple structure, it has this kind of so-called universal approximation property. And then also, the other part of this is that, so I didn't really say this too much, but these transformations that happen inside the neural network, these have parameters, and these parameters are what you learn. So when I said that you are using an algorithmic process, something like a continuous optimization technique like gradient descent, to learn a function. So what I really mean is that I'm finding values of those parameters that fit the data well. And this is possible to do in an efficient way using something like gradient descent because these functions are differentiable. So there are these two key benefits of neural networks, that they're super expressive on the one hand, and on the other hand, they're also differentiable, which allows for efficient learning using gradient-based optimization. Now, was that supposed to happen? Okay.
It's okay, now we can see.
All right.
I'm sorry, there's no way I can see you.
No problem.
Is there a problem when you look at the slides with light? No. It's okay for everybody? Okay, then we'll switch it on.
Okay. Yeah, I hope you got a chance to look at this slide because there's a funny thing going on here. So now, deep learning is fantastic because, again, the kinds of innovations that I talked about earlier with automatic drug discovery, automatic chip design, and numerous other things. Think Google Translate, think any computer vision system that's state of the art. They're all using neural networks, right? So deep learning is fantastic, but there are certain challenges, and I'm going to illustrate that with just this somewhat funny example. Now, I assume that most of you here have heard of ChatGPT, and if not, you should Google it right after this talk. So ChatGPT is run by a really powerful neural network, which has looked at a very large fraction of the text that is available on the open internet and learned to predict the next bit of text given a bunch of text that has been provided. So, of course, it's really powerful, but at the same time, sometimes, or in many cases, when you ask it questions or ask it to do tasks, it generates things that are extremely nonsensical. And here's an example of that. So you're asking a question that any human would be able to answer relatively easily, but when you look at this, you see that what's coming out is superficially very. It looks reasonable-ish, but then when you look at it, it's just meaningless. And there is a pattern here. So I don't know if you've been following what's going on with Microsoft's Bing search engine, which has now offered, which now has an option where you can chat with a ChatGPT agent, combining this sort of chatbots with search. And there are all of these stories on the internet about how it can do horribly wrong things, say horribly silly things that no human would ever. And the underlying issue over here is that this model is entirely driven by data. And this is data just pulled from the internet, and there isn't really a notion of what is true, what is the ground truth. And there isn't also an explicit notion of cause and effect. And to make it worse, whereas in a traditional software system, you could just pinpoint to some part of the code and say that, okay, this is the module that broke down, this is the part that needs fixing. Instead, here you have this massive black box with billions and billions of parameters, and there is no obvious way to debug. So then that raises this question for us, that if we are going to have a future in which AI is embedded into all of our scientific and engineering processes, broadly in society, which is where we are going, which is where all of these Silicon Valley companies would like you to go, how are we going to do that with an AI that is like this, that sometimes produces answers like this? And this is not just a one-off. There are deeper issues that are going on over here. So one fundamental issue is that deep learning is opaque. The algorithm is opaque. How it's going from data to some sort of a concept, that process we can't really see from outside. And so it's possible for the model to just converge to a concept that just doesn't really make much sense. It doesn't really connect to reality. At the same time, it's not interpretable. It's hard to debug and control. And also, the lack of domain knowledge, that means that everything has to be learned from data, and this process is often extremely expensive. You need a tremendous amount of data to train these models. And also, they can be unreliable. The training process can be unreliable. You can memorize all sorts of low-level stuff about the data that don't really, shouldn't really matter. Now, this is, again, I want to emphasize this. If there is one thing that I want you to take away from this, it's that AI is fantastic, but there are really, really serious challenges in applying AI, as the word is currently understood in large parts of the industry, in domains where you are doing anything real. This includes robotics, this includes healthcare, this includes finance, this includes programming tools. When you are doing programming, a little mistake in a keyword is not just an internet meme. It's something that can crash software systems. It's something that can kill people. So we have to be really mindful about these concerns about trust and reliability as we rush to deploy AI in real-world systems. Now, what we are proposing instead in this area of neurosymbolic AI, and more broadly in certain other segments of the AI community, is that we shouldn't really think of AI as just an an end in itself. We should imagine AI systems as part of a bigger process that involves both the human and the artificial intelligence. And so in the picture that I showed earlier, rather than having just the human brain or the AI brain, we should have a combination between the two. And how can we construct such combination, such effective collaboration? That is, to me, the next big challenge in artificial intelligence. And to me, this is something that would require essentially a new kind of programming. So if you think of what programming is, it's really a process by which humans control machines, right? And now we are talking about these machines that are autonomous, that are intelligent in some sense, that can learn from data. And what we need to have is effective means by which we can communicate our intent about what we want done, what we want learned, how the system should be structured to these algorithms. And that is what neurosymbolic programming is all about. Any questions at this point? I'll also take questions at the end, but if any of you have any questions, just stop me. I want to keep this informal. Don't hesitate. Okay, so then this is what neurosymbolic programming looks like. There are these two disciplines that are traditionally somewhat separated from each other, the discipline of deep learning and the discipline of classical programming. And we are imagining a field where these two sets of ideas come together in new ways. And if you're interested to learn more about this than what you can get from this talk, there is a book that we recently wrote on the title is Neurosymbolic Programming. You can find it on my website. And if you have any questions, also just feel free to follow up with me. Okay, so now let's dive a little bit deeper into what this area looks like. So let's start with the typical process of machine learning. So you're starting with some amount of training data, and you are starting with what's called a loss function. So loss function basically tells you, let's say that you have made a prediction, how correct or incorrect is this prediction? So you need some kind of a quantitative meaning of that, and that's what the loss function is. And you are also given a class of models. So this could be, for example, your neural networks or your decision trees. And then these two components, the loss function and the class of models, this is feeding into the learning algorithm, which is really an optimization algorithm where you're asking, what are the parameters of this model, the parameters of, let's say, this neural network, that's going to lead to the best fit between to the data set that we currently have. And that's really it, right? So you learn this optimization process. Sometimes it takes a very long time and a lot of compute, but eventually you converge, and then that's when you can deploy it in the real world and get something out of it. So what we are going to do is we are going to dive into two pieces of this. One piece is going to be these model classes. So far I've been saying that they could be neural networks or something else, but now what we are going to do is we are going to change that model class so that it includes ideas from classical programming as well as neural networks. So in other words, we are going to think about models that are combinations of traditional code, the kind of code that you would write as a programmer, with neural networks. And that's going to be the first part. The second part is going to be the learning algorithms that we are going to use such models. So again, this is a very important point. If you don't mind going back to just the slide before. Yeah, that one. So there are these two pieces. One is neurosymbolic model classes. So we are now thinking about going beyond just neural networks and instead thinking about really program-like entities where you have neural networks as pieces. Okay? So the appeal of this is that because this code is more human-like, with neural nets in specific places, but still the overall structure is often quite human-like, you have a means to understand what's going on. You have a way of analyzing the behavior of the system, and you have a way of connecting to human-engineered components. So it's really a representative of a sort of a collaboration between human-like language and this lower-level neural network language that is easier for AIs to understand. And then the second part is the learning algorithms. And these two ideas come together into this discipline of neurosymbolic programming. And again, why do we want to do this? Just to hammer it in, you have these two kinds of models that you could use to describe complex processes. One of them is traditional human-like code, what we'll call symbolic programs. They are interpretable, they are verifiable, they represent structured domain knowledge. There is no real learning needed, so it's data efficient. But on the other hand, with neural networks, you have the flexibility, the scalability of learning, and you have all of these great things that AI brings you. So we want to build a bridge between these two. And now, I'm going to give you just a couple of examples of what this looks like, just to make things concrete. So in the first example, we are going to have a composition of a neural network and a symbolic program that looks like this. So you have no longer just a neural network, you have an additive combination of these two things, a piece of symbolic code and a neural network. And this is a simple way in which these two kinds of artifacts can be combined. When you are thinking of creating a more complex system, you would imagine a lot of little compositions like this. You are going to maybe apply a combination like this in one place, then you're going to combine it with something else, and so on and so forth. And ultimately, this is a path towards building really complex systems with both neural and symbolic components. So I'm going to make this concrete by tying back to these applications in science and engineering that I talked about. So let's think about the problem of engineering a controller for, let's say, a car. In this case, it's going to be a toy car, but the same ideas apply if you're thinking about other kinds of robots or cyber-physical systems. So the thing is, human control engineers have solved this problem of writing controllers for a very long time. And there is this whole area called control theory, which gives you principles for writing these kinds of controllers. And so a very simple kind of controller is going to be something like this. It's going to be a program that's going to take in the current state, and then based on some functions, in this case, it's a so-called PID controller. So it's a combination of a so-called proportional term and an integral term and a derivative term. The details don't matter. The point is it's a function, it's a simple piece of code that takes the current state and the target state that you want to get to and gives you an action. So for the car specifically, the state could be your current velocity, the target could be where you want to go, the speed that you want to reach, and then the action could be acceleration or the steering angle. And so that's what a control engineer would write, and then you could imagine even having more complicated kinds of controllers where you have a branch, and then you are deciding that maybe you're going to do one thing in one branch and the other thing in the other branch. So in this particular example, what this says is that if the car is aligned with the axis of the track, then accelerate, otherwise slow down. Right? So this is just an example of a program that you could write, combining these basic control theoretic primitives in order to steer a car. Now, this is the classic pre-machine learning approach to control. The machine learning approach to control would be something like this, that you are going to learn a controller. So you are going to have a simulator, or maybe even the real world in some cases, which would be used to go and collect a lot of data from the real world. And then you're going to learn that certain kinds of behaviors are good, certain kinds of behaviors are bad, and then from that data, you are going to learn a function, that controller, the controller that takes the current state and gives you the action, you're going to learn it. And so you would represent it as a neural network, for instance, and then you are going to learn the parameters of that neural network. Now, there are these two different approaches, and the learning approach has this benefit that it doesn't require this deep engineering insight, but that's also its problem, that a lot of the times it turns out things don't really work out too reliably in a purely learning-based method. And so what we are proposing in this case, this was from a paper a few years back, is a combination, a linear combination of these two kinds of components. And one way to think about this is that you have a PID controller or any other controller that you have that's more human-like. But then you have this additional term, which is machine learned. And so why would I want to do that? So the thing about the human-written controllers is that they're often very conservative. They are designed with certain kinds of worst-case principles, and as a result, when you have some kind of special feature of the environment that you want to exploit, so for example, maybe you're doing a maneuver of some complex sort, if you just learned from data, you would be able to pick up some special trick that you could play in this particular scenario. But if it's a standard issue human written controller, you are not going to take advantage of this. Now, if you use a model like this, where you have a combination of the two things, one way to think about it is that you are, for the most part, doing what the standard human written controller is doing, but you are adding some extra flexibility that is learned from data, and this allows you to do more complex things. So for example, make more complex turns faster, and so on. And you see that there is a linear combination of these two things, and there is a weight which you can use to make this composition either more like the human written program or more like the neural network. And another way to think about it is that for those of you who are more familiar with machine learning, the symbolic information is being used as a regularizer to the machine learned model. So you are regularizing or injecting some prior knowledge into the learning process. So here's an example of what this idea looks like in practice. So if you think of this, if you look at this video, on the left-hand side, you have a car that is entirely driven by a neural network. On the left-hand side, you have this neurosymbolic, mixed car, and on the right-hand side, you have a car that is entirely driven by a neural network. So what you see is that as the training is going on, especially in the beginning, the neural network car is just behaving in a very erratic way. And the reason is, again, it has to learn everything from data. On the other hand, this regularized or neurosymbolic car, it has this benefit that it is using this prior knowledge, which is not, maybe the most sophisticated, race car driving kind of knowledge, but it is basic knowledge about how to run the car. And because of that knowledge, it can learn much more effectively from a small amount of data. It learns to do things in a more flexible way, in a more doing fancy maneuvers. That is the part where it's using the data-driven knowledge, not the basics of learning. And this is not the basics of control. And this is something that's a general pattern, that in a lot of cases, there is information that we have that we would rather just give to the model rather than having the model learn it from scratch. This makes learning easier. So if you're thinking of doing this in a real robot, interactions with the environment, collecting data from the environment is costly, and you can only do so much of it. So data efficiency is important, and also there's the reliability issue that the existence of this prior, it makes sure that there is some baseline of performance even before any sort of data comes in. Does this make sense? Any questions about this? Yeah?
Simple question. Have you tried, you said we can use the symbolic controller as a regularizer. Have you tried using it as a sort of mentor? Like maybe start with just the symbolic and then...
Yeah, we have follow-up work where we had this kind of a thing, where we had an iterative loop where there was a symbolic learner and a neural learner, and the neural network was getting newer and newer regularizers over time, and then the symbolic model was also getting informed by what the neural network found through exploration. So we have follow-up work which does exactly that sort of thing. Yeah? So infinite training data is a situation where I would imagine the neural network would do just fine, but that's also not a situation that is realistic, especially if you think of physical agents. You can get a lot of training data in the simulator, but when you are getting into the physical world, there is only so much information you can collect. And not only that, but the information that you collect has to be safely collected. You can't, for example, just take a car, like take a Mars rover, run it all around Mars, have it go down a few cliffs, and then just spawn it back up. The car is going to be a crash before you can do that. So I think that it's very important in real world settings to think about low data performance of learning under small amounts of data. And that's a place where I think these sorts of symbolic priors can really help.
Do you still think that the amount of training the pure neural network will win? Because it will always be overfitting, even if you have amount of data. You can eliminate the overfitting.
Yeah, so there is a separate.
Maybe actually the other model will win.
Yeah. So there is a separate question of distribution shift, which is that when you're talking about infinite amount of data, the data from what distribution, right? So a lot of the times what happens is that there is a gap between, actually in the simulation reality situation as well, there is a gap between what you see during simulations and what you see during reality. So one of the problems that we found, I don't have a video for this here, but the neural network is very sensitive to really low-level features of the environment. You tweak the environment a little bit, and then the card just crashes. And that is something that you're going to face pretty often in the real world.
The lambda that was mentioned before as a hyperparameter, and furthermore, how do you handle end-to-end prediction? I mean, do you train separately the small neural networks that use in conjunction with symbolic models? And I mean, I think that the colleague just asked a similar question, but how do you manage to find where there is a sort of a good trade-off? I mean, how do you decide where to put the symbolic?
Yeah, so there is a rigorous treatment of this that thinks about that lambda as something that's selected by an adversary, and you are really solving at that point kind of a min-max problem, and there is a way of handling that. But for practical purposes, what we have found is that it's enough to try out, iteratively reduce lambda. You're starting with something more, biased towards the symbolic side, and then progressively adding more and more neural flexibility.
And is changing the symbolic part really possible? Like, for example, you mentioned earlier that it is possible to use it for better observability. Say, an issue happens in production, and then you would probably want to change that. So, is it just that you reuse some of the already trained neural network, small neural network models, and then just tune the hyperparameters like lambdas? Like lambdas are hyperparameters. I mean, do you reuse something, or do you?
Yeah. So you could imagine having starting with the same weights that you found for the previous value of lambda. So there is a principled algorithm where you can iterate over the lambdas, and you can do that sort of sharing. Okay, thanks. Yeah?
Another question. You said the model, the neural network model was very sensitive towards basically low-level noise.
Yeah.
Is this like in an adversarial sense? And if so, have you tried using the same sort of symbolic models to, I don't know, do some sort of robust trading?
Yeah, that's exactly what I was alluding to. So what we found over there is that in the reinforcement learning setting, which is where this is at, typically people just train and test in the same environment. But if you modify the environment, then that can completely throw off the neural model. But if you have a neurosymbolic model, then it's possible to at least have a certain baseline flexibility, functionality, and then adapt the neural part. So it's a way of introducing robustness to the model. Yeah. How are we doing in terms of time?
I think 6:43, so I should be the position.
Okay. A different way in which neural and symbolic pieces can be combined is something like this. So you have some neural pieces in the beginning, and then you have a symbolic layer on top. And one area where we have applied this, again, going back to the science and engineering thing, so we showed an example of an engineering application. This is a scientific application. So we have been exploring these sorts of learning-based methods in the setting of a range of natural sciences, and in particular, behavioral neuroscience. And so there, you are starting with videos of lab animals, and you have a lot of other kinds of information as well, like you have measures of neural activity, you have data from pharmacological evaluation. And from all of this, what you're trying to do is you're trying to develop an understanding of how the world works. How do these animals function? So a particular example of this is something like this. You are starting with these videos of lab mice, and you are ultimately trying to learn what kind of behavior is taking place. And now, by the way, you can replace mice by other organisms, including humans, but of course for humans we don't have this sort of data. Here, what we want to do is to look at videos and generate these sorts of labels as to what kind of behavior is going on. Are they attacking, are they sniffing, and so on and so forth. One way in which neurosymbolic programming comes in here is that interpretability is really a crucial thing here, right? We don't just want to get a neural network that does these predictions. We want to understand how the world works. And to that end, having a symbolic model is really helpful. And so something that some of our colleagues and we also did in some recent work is something like this, where you have, you write a little program that captures some high-level knowledge about what is going on. So in this case, imagine that you have some sort of a computer vision model that is a neural network that is giving you, some trajectories of these mice, which is that, over a period of time, what are the important points in the mice's body. And that's something that you see in the bottom. And then what we want to do is we want to predict what sort of behavior is going on. Now, doing this from just raw data is difficult because of the shortage of data, but also we want to have interpretability, we want to have consistency with domain knowledge. And what some work in this space did is that there is the human expert, the scientist, writes a little piece of program. So here, for example, you have something about what is a distance measure between the noses of two mice, and this is something that's written in terms of code. And then in a second phase, what you do is you use this sort of programs to structure the representation learning process. And what is the representation learning? This is the bread and butter of deep learning, where you are starting with some low-level signals, and you are computing this abstract representation of what is going on in this picture or this other kind of data. And so in particular, I won't go into the details too much, but basically you have these two different loss functions. One of them says that I want to learn a latent representation, this abstract representation, in a way that can be decoded back to the original trajectory, the original behavior of the mice. But the other one says that this is consistent with this higher level expert knowledge about what distances mean in the physical world, and you could add other kinds of scientific knowledge as well. So essentially, this is modifying the loss function, the objective function that is used for learning, in order to be more consistent with human-held domain knowledge. And so over the last few years, whole science is developing over here. There are different kinds of compositions of these neural and symbolic pieces that are coming out. And for example, we have if-then-elses, where some part is symbolic, some part is neural. You have symbolic after neural. I already showed that. There's neural after symbolic. So collectively, these sorts of compositions define a programming language of combinations between neural and symbolic pieces. So in the time that remains, I'm going to give you a brief overview of what learning looks like here. I'm going to have to skip a little bit of material because of time, but I hope that I'll give you a sense of what the problems are. So again, the question that we are now trying to address is, okay, great, so you have these sorts of composite neural symbolic models. How do you learn these from data? If it was neural networks, I would just use gradient descent, and that's very efficient. But now you have these symbolic pieces as well. And I don't just want, necessarily, the symbolic pieces to be fixed by an expert. We also want some of the flexibility in the learning process to be applicable to even the symbolic piece. So I would like to synthesize or automatically generate the symbolic parts of these programs too, if possible. So how do we do that? And it turns out that there's a whole discipline of program synthesis which is studying questions like this, and the goal is to bring together this world of program synthesis and the world of differentiable machine learning. And so this is what the problem statement looks like. So now our learning algorithm takes in two things. So it takes in the data. It also takes in a so-called programming, a domain-specific language, which is essentially a big space of these possible programs that you could have, these programmatic compositions of neural and symbolic pieces. And then you have some sort of an objective, and your goal is to automatically discover a program in this language. So that is the neurosymbolic learning or neurosymbolic program synthesis problem. And so in particular, the example would be that for that car controller example, I would be defining a grammar, in a symbolic notation. I would define the space of all possible programs that you could write. And again, the details don't necessarily matter, but think of it as, you are fixing some space of programs that could represent things like, the program that we saw earlier. And we would want to discover these kinds of programs automatically. Again, I'll skip the details of the language in the interest of time, but basically it's, you know of programming languages like Java or Python. This is a more restricted programming language that is suitable for, experts in some domain, like neuroscience or control and so on. And the motivation is that I want to automatically search through the space of programs in this language and find one or more that suits me. So then overall, the picture looks like this. You are starting with a learning objective. You have a learning algorithm, and you have a neurosymbolic program that you are getting out of this learning process. And that program has two pieces. It has some parameters, just like with neural networks, and it has also a structure. This is the symbolic piece. That's that alpha over there. And then after you discover this program, you may do some further downstream analysis, and this process can go on. So the overall learning problem then becomes this kind of an optimization problem where you now have to search for this symbolic structure, this alpha, along with the parameters theta. And then you are solving something like this, an optimization problem. What this says is that find me an alpha, the symbolic structure, and also find me the parameters of the neural pieces so that that objective function is minimized. So that's the overall problem statement. Are there any questions about that? Yeah?
The GPT chatbot, something like that, because it has some algorithms for about, let's say, gender issues, religious issues, let's say, body.
Yeah. So the part that's missing is that in ChatGPT, it's a transformer. It's a particular neural architecture. Whereas here, you have a range of possible shapes of these symbolic programs. And you can imagine, many different ways in which you can compose together the different symbolic pieces. And you are really searching over the space of all of those possibilities. Does that make sense? Yeah, so there is this discrete part of the problem in addition to the continuous problem. And by the way, in that objective function, there was this S alpha term. It just means that you are disfavoring, really complex kinds of programs. Okay, so then how do we actually solve this problem? What time is it?
You had 10 minutes.
Okay.
12 minutes.
Okay. So I'll actually skip some slides. We can skip this one.
15 minutes.
Okay. So let's start with this one. So how do we solve this problem where there is this, program structure as well as the parameters of the neural networks? And so one way to do this is to think about, the space of programs as being this graph in computer science terms. It's a network of nodes and edges. So you can imagine a process that is starting with, zero code and progressively adding more and more code. You can think of that as you are at a certain node, you're following an edge, and you're going to, more complete programs. So this models the process of writing a piece of code step by step. And so, for example, you can imagine that, let's say that you started with this little piece of code, you had these 2 assignments, and then you added some extra code to that, and this process, went on, and over time, you reached some complicated program, and that may have some neural pieces. Then you train the neural pieces of that program. So you could imagine something like that. Let's carry on. Okay. So the problem with this kind of search is that the space of programs is very, very large and quickly explodes. So if you just want to get a sense of it, think about the little language of these control, PID controllers that we talked about. So I said that, okay, maybe you can have 2 branches, you could have an if then else, and you could have one possibility along one branch, another possibility along another branch. But the number of such programs quickly explodes because you could have many, many ways in which you could split those branches. You could have many different conditions. And more generally, you could have much more complex programs. So then the question is, how do we speed up this process of search? How do we make things scale? And that's where, again, we lean on the power of deep learning, that the idea now is that we are going to guide this search process using neural networks that are learned from data. So what does that look like? So you can imagine now a function that is telling you basically that you are at a certain point, you have written a part of the program. What is the next piece of code that you are going to write, or how are you going to extend it? Imagine a neural network that is able to guide this process. And so you could imagine something like this. At each point, the neural network tells you what piece of code to write next, and this process goes on, and at the end, you arrive at a complete program, you train that program, the neural pieces of the program, and you get some value, meaning that, how good is this program? Should I keep it or should I throw it out? So how do I actually do this? There are interesting algorithmic ideas. One idea that I'm going to actually skip, let's maybe go past this. I'm going to skip this in the interest of time. You can keep going. Okay, let's maybe stop here. So here's the issue that you have with these kinds of neurosymbolic programs. So we are saying that we are generating a program step by step. And at each point, you have this partially complete program. You haven't seen the whole of it, right? And that program can lead to a lot of different kinds of code, some of which are good, some of which are bad. But it turns out that there is a way in which you can learn what is the best value that you could get by taking a certain decision. And this is called a value function, and this is something that you can learn in the form of a neural network. And then that neural network you can use to guide the process. Actually, we should just go past this as well. You could go past this. Yeah, so let's talk about this. So you are starting with a piece of code that is wholly unfinished, and then you are progressively adding these pieces of code. So the details of what's there in this code doesn't really matter. What matters is that you have these edges that tell you that the program is getting more and more full with code over time. And so what you can do is, if you have an incomplete program, it turns out that you can think about the piece that is missing, and you can approximate the best possible value that you can get by any possible ways in which you can complete that incomplete piece using a neural network. How do you do that? Well, if I had some more time, I would have given you more details. But basically, what this allows you to do is you can prune out certain branches. You can throw out certain parts of this search space, and you can focus your search on certain more profitable paths. And all of this is a principled optimization algorithm with guarantees, and that's something that, if you have questions about how exactly this works, follow up with me, I'll tell you. Okay, so this is the underlying algorithm that we use. This is a classic symbolic AI method called A-star search. This goes back 50 years before machine learning became a thing. And so really what we are seeing here is an algorithm that combines this sort of classical symbolic search-based method where you're operating in a discrete space using these algorithms like A-star. By the way, this sort of strategy was used in the original Deep Blue AI that beat Kasparov back in the day. But then we had this shift to more deep learning based methods. But now here's an example of how these ideas can come together. So in summary, what this looks like is something like this. You produce the program step by step. If you have an incomplete program, you fill the hole with a neural network. And then through some magic, you find a lower bound on what the most value is that you can get along this branch. And then you use that to prune the search space. So this is something that empirically works really well. We have compared with other approaches, and I'll spare you the details, but essentially this approach is able to find performant programs a lot more effectively than competing approaches. So as I said, there is a taxonomy of different kinds of neurosymbolic architectures, compositions of neural and symbolic models that's emerging. Likewise, there is also a big space of algorithms that combine neural and symbolic ideas that are coming together for learning these kinds of programs or systems. So we talked about, the method that I talked about, it can be thought of as neural guided search. You are using a neural network to guide a search process. It turns out that internally, it also uses something called relaxation. And there the idea is that you're trying to find a program which represents a function from input to output. But imagine approximating that program by a neural network, which is also a function from input to output, but it is a differentiable function. So you're approximating a potentially non-differentiable function by a differentiable function. And then it turns out that this has a lot of advantages in terms of search. There are methods where we are going the other way, where we are learning a neural network. So imagine that you're trying to find a program. So what you could do is you could learn a neural network that kind of sort of approximates what the program does. And then you distill that neural network into a program. So an example would be, let's say that you are trying to learn a program to drive a car. You first learn a neural network that gets sort of close to running the car, but it's not maybe robust. And so after you've gotten that neural network, you distill it into a program, which means you're finding a program that approximately does what the neural network does. There are also approaches where you are learning new programming languages altogether. So for example, let's say you're in a new domain, you are going to need new primitives. So for example, I said PID control. This is something control theorists came up with. But imagine that you are an AI that's been deployed in a bunch of new control tasks without that prior knowledge. Could I automatically discover this PID controller primitive? Could I progressively discover all of control theory, or really any theory for any domain that you're interested in? Imagine that I'm showing a neurosymbolic AI how to do math proofs. It sees set theory, it sees group theory. Can it learn then primitives that are then reusable, that can be used to build new programs, new proofs for in these theories? So these are some of the questions that are out there. That's the component discovery. There's also symbolically guided deep learning, where you're introducing some symbolic knowledge into a deep learning process. An example would be that neuroscience application I talked about earlier. So we'll skip through the next few slides. This is just details on what these methods are. I want to go back to the high level again. So what I have shown over here is that there is this new discipline that is coming together where you have a combination of two different fields. You have the field of programming languages and symbolic AI, which all trade in these, how do we do reasoning? How do we work with algebraic expressions and identities and code written in human-like notations? How do we give guarantees about that? And then there is the discipline of data-driven machine learning. So what we are seeing is increasingly there is this confluence between ideas from these two spaces that you are seeing, new ways of bringing together models where you have some neural pieces and some symbolic pieces and new kinds of learning algorithms that bring together deep learning and this sort of symbolic search over programs. And there are many patterns that are emerging, both on the side of how you are building these models and also on the side of how you're searching. And the next few years, I think, are going to be really exciting as to, I expect that we'll see new kinds of algorithmic methods that emerge, but also practical deployments. There are several groups that I know that are actually trying to deploy these sorts of methods in startups and big companies, and things are moving very fast. So what I would say at the highest level, though, is that machine learning is a revolution. It is changing and will continue to change all of science and engineering and more broadly human society. But it's not going to be machine learning alone. It's going to be a combination of human wisdom gathered over the centuries and the power of algorithms to learn from data. How do we build these sorts of human-machine hybrid systems? This is something that is, I think, the next big challenge in AI. How do we build systems that are trustworthy, that humans can work with, deploy in safety-critical applications? This is the next big challenge. And then what I've shown is that there is a science that is emerging as to how to build these sorts of hybrid, neural symbolic systems, but there are some other approaches that people are thinking about as well. But at the end, we humans, we express our thoughts using language, and the reason why we discovered mathematics is because that is the way in which to do complex things, if you're a human. So before Einstein, Newton and Leibniz discovered calculus, we were not exactly making these kinds of modern machines that we are today. So we need all of the power of those symbolic notations, but we also should make use of all of the power of machine learning and data. So how do we bring these two things together? This is going to be the next grand challenge in AI, in my opinion. And I have there another failure of ChatGPT, but you can just, it's like shooting fish in a barrel. You could just search on the web and you'll find lots of examples. And yeah, so it's just that these two kinds of approaches have different complementary advantages, and there's a lot of value in bringing them together. And with that, I'll end, and happy to take questions.